Hello everyone. In this video, I want to go over 3 commonly used built-in data structures in Python. Those 3 data structures are lists, tuples, and dictionaries. In a previous video, I went through some details of lists. In this video, I want to review some of those details or introduce them if you're new to lists, and then talk about how tuples are like lists but slightly different, and then talk about a brand new data structure, dictionaries. So first, let me explain what do I mean by built-in and what do I mean by data structures. Well, by built-in, I mean these 3 data types, these 3 data structures are available for use right out of the box with Python. We don't need to import any modules in order to start creating lists, tuples, and dictionaries. They are that standard in Python. By data structures, I mean a way of structuring data for organization, storage, and access purpose. Now, there's a large field of data structures in computer science, and I'm not going to go into detail into that field or talk about really any complicated data structures or how to implement them. We're just going to stick with these 3 commonly used ones. So lists, tuples, and dictionaries are all used to structure data so that you can store it in a very efficient manner, and you can access the data in that structure in an efficient manner. These 3 data types are typically used to solve common problems. That's why I call them 3 commonly used data structures. All right, let's start with the first one, which is a list. So a list is a sequence of items. Lists are zero-based for indexing, which means that each item in a list has a position assigned to it that starts at 0 from left to right. I'll also note here that lists are mutable, which means they can be changed. One more thing I want to note about lists before we start working with an example of them is lists have an order to their items. Okay, these are probably the 3 most important big picture things to know about a list. Each item has a position, the items cannot change, and the items are in a certain position because they have order to them. All right, so let's start with an example. Let's say I have a list of integers, and I'll just call it nums for simplicity. And I'm just going to make up some random values and put in this list here. All right, there's some random integer values. I'll note that in Python, we can have mixed types in our list. Right now, all of my items are ints, but if I wanted to, I could put a float in here, or I could put a string in here. They can be mixed types, but right now, all of my items have the same type, which is int. So I can print out nums, and I'll see an output representation or a string representation of my list. All right, so I said that lists are zero-based for indexing. So let me write over the top in a comment what index position each one of these numbers are at. So 0, 1, 2, 3, 4, and 5. So the 3 is at index position 0, and the 7 is at index position 5. There's also negative indexing. So the last element or the last item in your list is at index position -1. The second to last is at -2, and so on and so forth. So that means that the first item in your list is at index position negative length or negative count, which is the number of items in your list. So let's take a look at indexing. So if I print out nums sub 0, I'm going to see the 3. If I print out num sub 0 and say num sub -6, I'm going to see 3 twice because there are 6 items in this list, so -6 also represents the position of the 3. Let me print out another one. Let's do nums sub 0 to 2. This is the slice operator, and this is going to take a slice from index position 0 inclusive to 2 exclusive. So we're going to see a sublist of nums, which is 3 to 6. Awesome. Next, lists are mutable. So lists are mutable, which means they can be changed. If I want, I could append an item to the end of the list. So I could do nums.append and say I want to add 100 to the end. And then I'll see 100 be the new last element in the list. I could remove an item as well. So let's say I want to remove the first occurrence of the 7. I can do nums.remove. And as you can see from the little documentation hover dialog here, it says list.remove value will remove the first occurrence of value. Perfect. I want to get rid of that 7. I'm going to print out nums, and the 7 is now gone. All right, lists have an order. Lists have an order to them. As you can see, we have these unique positions. As you can see, when we add an item, it goes to the end when we use append. When we remove an item, then all of those numbers are going to be moved over to the left to kind of backfill so that we're always keeping track of the order or preserving the order of our items. So that means we can sort our items in our list. So let me print out list one more time. And then I'm going to do nums.sort, which is going to do an in-place sort from low to high. And I'm going to print out nums again, and we're going to see that the order is actually going to be changed, but that order is going to persist. From line 27 and beyond, when I work with nums, this is going to be the inherent ordering of my numbers. So we've been working with 1D lists. And 1D lists, you can think about them kind of line-like, right? They're flat, they're linear. Let's move on now to 2D lists. And 2D lists, you can think of them like grid-like. Okay, so they're kind of getting some dimensions to them beyond a line, kind of like a plane, like a Cartesian plane, right? You have your X and your Y axis. You can think of 2D lists like a grid on that axis. 3D lists, these are cube-like. Think about adding kind of a Z dimension to that XY plane. 4D lists get increasingly difficult to visualize. So I'll say kind of 4D to ND lists, kind of dot, dot, dot. I highly recommend that if you have 4 or more dimensions for your lists, you probably need to reevaluate. Do you really need that many dimensions, and can you flatten your data structure in some way? Perhaps break it up into 2 different lists and then link the list together by some sort of identifier. I think that'd be more appropriate because beyond 3 dimensions, lists are increasingly difficult to work with and visualize what's going on. So 1D lists we're pretty familiar with, especially if you've watched my previous video introducing lists. Now let's talk about 2D lists because this is where things can start to get a little bit more complicated. So when working with a 2D list, I like to introduce them by saying there are 2 main ways to think about 2D lists. And which one you use when you think about 2D lists is up to you. So if one sinks in more than the other, then stick with that as you're learning to work with 2D lists. So the first one is to think about 2D lists like a table. So if you've worked with an Excel spreadsheet before, this analogy might be helpful for you. So when I say like a table, I mean it has rows and it has columns, or it has an x-axis and a y-axis, okay? This kind of thought process. Let me draw a picture to help explain this. Let's say I have some data in a matrix or in an Excel spreadsheet, and let's say the data is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, I've drawn this data into a natural grid-like structure, right? I have 3 rows. Rows go this way, kind of on a horizontal axis. And I have 3 columns, and columns go this way on my vertical axis. Another way I could say this is I have 3 entries on my y-axis, right, going down my plane, and I have 3 entries on the x-axis going across the plane. All right, what I want to do is I want to draw the indexes for each one of these numbers on the rows and the columns, or the y and the x-axis. So on our rows side, we have row 0, row 1, and row 2. On our column side, we have column 0, column 1, column 2. If I want to get any of these black numbers out of our grid or out of our 2D list, I'm going to have to uniquely identify its position in terms of both its row and its column. So let's try this. Let's say I want to print out the 1. Okay, I can have a print statement where I'm accessing nums, or better yet, let's call this matrix. Okay, first I need to index to get the row. So I want row sub 0. And then next I need to index into the column. So row sub 0 is this whole 1D list right here. If I index into this list at 0, then I'm going to get the 1. Let's try another example. Let's say I want to get the 6. All right, what am I going to print out? Well, first I'm going to index into matrix to get its row. 6 is in row position 1. Then now I have row position 1. That's the 1D list with the numbers 4, 5, 6. I'm going to index at column 2. And this is going to give me the 6. So this is one way of looking at 2D lists. You restructure the list such that it's in a grid-like or table-like format, and then you label your rows, zero-based indexing of course, and you label your columns, also zero-based indexing. When you index into your 2D list once, like we've done here, you get a row. You index again, you're indexing into that row. At a column, you index twice into a 2D list, you get a value in that list. All right, let's try it out in code. So let's say I have matrix, and matrix is going to be a 2D list with those same numbers that I was drawing in our diagram. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so here's matrix, and I want to print out matrix sub 0, sub 0. Well, this is going to print out 1. Now I want to print out matrix sub 1, sub 2, and this is going to print out the 6. All right, let's try the second way of thinking about 2D lists. The second way to think about a 2D list is a 1D list where each item is a 1D list. So essentially this is the nested lists approach. So I'm going to define matrix again, but this time I'm not going to define it such that it naturally looks like a grid, because that was only to help me, the programmer. I don't have to define this 2D list in this particular formatting in Python. So I'm going to have a list where each item in the list is a 1D list. Okay, so my first item is going to be a list 1, 2, 3. My second item is going to be a list 4, 5, 6. My third item is going to be a list 7, 8, 9. So this looks linear, right? This looks flat. It's one-dimensional because it's on one line. And this is really a valid way of looking at a 2D list, because how this is stored in memory is actually more linear than it is grid-like. So visualizing a 2D list as a grid more helps us, the programmer, than something that Python needs us to visualize in order for us to program in Python. All right, so let's say I'm going to print matrix sub 0. Okay, so remember, matrix is just a 1D list where each item is a 1D list. So what do you think the type of matrix sub 0 is going to be? If I slap type around here, it's going to print out list. If I do, let's say, type of matrix sub 0, what do you think is going to print out? Well, matrix sub 0 is the item, what I've highlighted here, which is a 1D list. I index into that 1D list at index position 0, I get a 1, so the type we should see is int. And we do see int. So these are two different ways for looking at a 2D list. Use whichever one is more helpful. I think drawing your 2D list in a grid-like structure and then labeling your rows and columns can really help get started. All right, for 3D lists, I'm not going to do a very comprehensive example because it's really just generalizing our 1D and our 2D lists. So for example, maybe I have a cube. It's a list where each item in the list is a list, and each item in that list is also a list. So maybe I'll do a 2 by 2 by 2 cube. So let's do, say, 0, 0, 1, 1. Okay, so right here, this is one item in my cube list. It is a 2D list that has 2 items. So now I'll have another item in my cube list, which is going to be a 2D list. So it'll have 2, 2, and 3, 3. So this is a 3D list. It has 2 nested lists in it, right? So first, it has this 2D list and this 2D list. And then let's do the first 2D list. This 2D list has 2 items in it, which are each one-dimensional list, and that one-dimensional list is of integer items. All right, we're not going to do anything else with 3D lists. If we need to use them in the future, we'll spend some more time with them. But just know that anytime you have an n-dimensional list, you've got to index n times in order to get a value. So I'd have to index at, say, cube sub 0, sub 0, sub 0 in order to get this first 0 here. Now it's time to move on to our second built-in data structure, which is a tuple. And a tuple isn't going to take too much time to go over because a tuple is an immutable list, which means it cannot be changed. So we declared lists using hard brackets, these kind of square brackets. In order to declare a tuple, we use parentheses, or we don't use anything to group our comma-separated list of values at all. So let's try this out. I'm going to have my tuple, and I'm going to assign it, say, the strings x, y, and z. I'm going to print out my tuple, and I'm also going to print out the type of my tuple. All right, so I didn't put any parens around my tuple when I declared it, but when I print it, I'm seeing parens around my strings. This is denoting that this is a tuple. When I print out a list, I see the hard brackets or the square brackets denoting this is a list. Okay, so when you see these parens, think tuple. And we see the class here of type tuple. All right, so this is an immutable list, right? So that means that I cannot change any of the values in my tuple. What happens if I try? I'm going to try. Let's do my tuple, say sub 0. I no longer want it to be a lowercase x. I want it to be an uppercase x. Well, I'm going to run this, and I'm going to get a type error. It says, tuple object does not support item assignment. I cannot assign to an item in my tuple a new value. All right, let's go through a few more examples of tuples and how they're a little bit different from lists, and then we'll move on to dictionaries. So when declaring a single item tuple, you have to have a comma after it. So for example, if I wanted a single item list, I could just do this, but I can't do this because this is going to use the parentheses like the operator for precedence, like remember your PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. This is going to use parentheses as kind of an arithmetic operator. So what I have to do is put a comma after that single item in order to force this to be evaluated as a tuple declaration instead of an arithmetic expression. So let's do my single item tuple. Let's print it out. Should comment this out so that my code runs. And there we see our tuple. If I take this comma off, this is not a tuple anymore. This is just the integer one. Okay, so keep that in mind. If you ever need to create an empty tuple, you can't simply do open paren, close paren for the same reason that I gave up here. So what you need to do, let's do my empty tuple, is invoke the tuple initializer or the tuple constructor. So you type the name of your class and then open paren, close paren, and this is going to create a tuple. All right, I can print out my tuple. We'll take a look at it. There are no items in it. Tuple indexing and slicing is the same as for lists. Nothing new there. So everything that we did up here with our indexing is going to work the same for tuples. That concludes our introduction to tuples. They really are just like lists, except they cannot be changed. You might ask, well, why would you use a tuple then? Well, perhaps you do have a fixed set of values that's never going to change. It can be more efficient to use a tuple. You're actually using a tuple when you return multiple values from a function. You have a comma-separated list of values after your return statement. Those are going to be packaged up into a tuple, and then the tuple object is going to be returned. And if you don't unpack using a comma-separated list your return values, you could just store all of those return values in one tuple just by having a single assignment for your return value when you call a function. So there's one place where tuples are used inherently built into Python, and that's with returning multiple values. I encourage you to play around with what I just described, and I think you'll have some fun with it. All right, our next topic, dictionaries. I love Python dictionaries. I get pretty excited about some things, but I get really excited about Python dictionaries because they're so easy to work with and they're so valuable. I find myself using dictionaries all the time. And I think that as you progress in your Python and or your data science career, you will find yourself using them quite a bit as well. So what is a dictionary? A dictionary is a list with keys as indexes and values mapped from those keys. So what do I mean by keys and values? Let's first talk about what is a key value pair, okay? So a key value pair is where you have a value and you use it to look up another value. So this key value could be anything, but keys in a dictionary must be unique. Meaning you don't have any duplicate keys. You've actually probably worked with keys quite a bit in your life before. Like for example, if you're a student, you probably have an ID number. Your ID number is unique to you. There are no two students at your school who have the same ID number. Otherwise, that would defeat the purpose of an ID number, right? So in this case, a student ID number is a key, and that key is used to look up a value, or in your case, a set of values, right? There's a lot of data associated with your student ID, like your name, your number, your home address, your GPA, your transcripts, all sorts of things are associated with your student ID. Those values don't have to be unique, right? Like there might be people at your school who have the same name as you, right? If you have a common name like Katie or John, there's a lot of Katies and Johns out there. I'm not saying that you're not unique, but I'm just saying that your name is not necessarily unique, but your ID number is unique. So this is an example of a key, a student ID. So an example of a value then would be your student name. So if I look up, say, ID, I don't know, 1, 2, 3, 4, 5, that could map to, let's say, Jane Doe. So here's a key value pair. 1, 2, 3, 4, 5 and Jane Doe is a key value pair. The key is unique, 1, 2, 3, 4, 5, an ID number, which is used to look up the value Jane Doe. All right, let's start working with dictionaries in Python. So we declare a dictionary in Python using the curly brackets. So we've seen parens for tuples, we've seen hard brackets for lists, and now we're going to see curly brackets for dictionaries. So let's have my dictionary be initially an empty dictionary. Okay, there are no key value pairs in this dictionary. I'll print it out and we'll see that there's nothing there. It's empty. Another way to initialize a dictionary is like how we initialized tuple. We could do my empty dictionary is assigned dictionary open paren close paren. You can also do this with list. Just show you real quick, list. It's another way to initialize a list. Okay, so we've got this empty dictionary. We're not going to do anything with it, but we are going to do some work with my dictionary. So let's say I want to model this student ID to student name key value pair. So I can add a new value to a dictionary using hard brackets, my key, so let's say the key is 1, 2, 3, 4, 5, and then assignment, I want to assign to this key the value Jane Doe. Now let me print out my dictionary, and we're going to see that it has one entry, the key value pair 1, 2, 3, 4, 5, mapping to Jane Doe. All right, let's try another example. Let's say we want to initialize a dictionary that's not empty, and it's going to store some state capitals for the states around the area. So let's call this dictionary state capitals, and I'm going to initialize it to have the following key value pairs at the same time I declare this dictionary. So it's not going to be empty initially. So Washington is the key. Its value is Olympia. I'm going to use a comma to separate my key value pairs, just like I would to separate my items in a tuple or a list. Let's do Idaho, which maps to Boise. And let's do Oregon, which maps to Portland. So when I initialize my list, or excuse me, when I initialize my dictionary, I'm using the colon in order to separate my key value pairs. Let me print these out. And we see our dictionary. Dictionaries are mutable, which means they can be changed. So if for some reason, let's say Washington's state capital changed to Spokane, where I live and love, I could update the value for the key Washington to be Spokane. And there we see Washington maps to Spokane. I'm going to comment this out just so people don't think, I actually think that the capital of Washington is Spokane. And I want to go through, of course, a few more examples with this state capitals here. I could add another state capital to our state capitals dictionary. Let's say now I want to add California. So just like I did up here with Jane Doe, I'm going to add another entry to my dictionary. And let me see if I can spell California right. And the capital of California is Sacramento. Let's print this out. All right, so far, all of the key value pairs that I've been entering into my dictionary have been printing in the same order I've been entering them in, which is kind of coincidence. I don't want you to think that dictionaries have an inherent ordering like tuples and lists. So I'm going to be very clear here that the key value pairs in a dictionary are not ordered. Okay? There's no guarantee on the order of your state and capital key value pairs in the state capitals dictionary. They just happen to be showing up in this order. Now let's see an example of how we can initialize a dictionary using a list of tuples. So let's do an example with Roman numerals. Maybe you remember your Roman numerals from high school or middle school. All right, so I'm going to have a new dictionary, and I'm going to pass in a list. Each item in this list is going to be a tuple. Specifically, it's going to be a two-item tuple, where the first item in the tuple is the key, and the second item in the tuple is that key's value. So here's our first one. So Roman numeral I, this maps to 1. Our second one, Roman numeral V, this maps to 5. Our third one, Roman numeral X, this maps to 10. And our last one, Roman numeral L, this maps to 50. Okay, so I can take a dictionary and initialize it using a list of key value pairs, where a key value pair is, in this case, is structured as a tuple, a two-item tuple. So this is just really cool, right? This is another way to store our data. Okay, here I'm storing it as a list of tuples, and now after line 93, I have Roman numerals, and I'm storing that same data as a dictionary. Okay, so you have choices often with how you're going to store your data. What data structure are you going to use? Some are more inherent to work with for your type of data than others. Like this is kind of clunky to work with, right? But this is beautiful to work with. So Roman numerals, at least the mapping, is naturally stored well using a dictionary. If we wanted to, we could take this dictionary back to a list of tuples. Let's take a look at how we could do that. So let's do Roman numerals as list. This is going to be assigned a new list. Okay, so I'm creating a list, and I'm going to pass in Roman numerals dot items. And now if I print out Roman numerals as list, I've got that list of two-item tuples back again. So there's a way to take a list to a dictionary and a dictionary back to a list. All right. Some more general notes about working with dictionaries. The types that you can use for keys include integers, strings, files, tuples, etc. I want to emphasize that lists cannot be used as keys. The reason why is lists are mutable. They can change. That's why they cannot be your keys in a dictionary. And then your types for your values can be any type, anything. There's no restriction on that. Next, let's see how we can figure out how many items are in a dictionary. Len works with tuples, lists, and dictionaries. It'll tell you the number of key value pairs when you're working with a dictionary. So let's go back to our state capitals example, and let's see how many items, how many key value pairs there are in state capitals. There are 4, right? So I've got the key Washington, the key Idaho, the key Oregon, and the key California. I can check for the existence of a key. So I can print and see, true or false, is Washington a key in state capitals? It should be. I get a true. There it is right there. Let's see if Olympia is a key in state capitals. It shouldn't be, because Olympia is a value, not a key. I could see if Olympia is a value in state capitals by adding dot values on the end here. That's true. Dot values will give you a list of all of the values in your dictionary. There's also a dot keys, which will give you a list of all of the keys in your dictionary. Let's see how we can loop through the key value pairs in a dictionary. So I could have for state in state capitals, and I could print the state, and I could print state capitals substate. So effectively what I'm iterating over is the keys in my dictionary. Remember the for in template, for item in sequence? Well, our sequence here is state capitals, but remember this sequence, I'm doing kind of finger quotes, this sequence doesn't have an order, okay? There's no explicit ordering to key value pairs in a dictionary. So here I'm printing out my pairs as such. If I want, I could have my item be a 2-item tuple, which is a key value pair. I could do for state comma capital in state capitals dot items. Let me just change my formatting here just a little bit so it's obvious in the output. All right, here's our output from lines 110 to 111. So what I'm doing is I'm iterating over a list where each item in the list is a 2-item tuple. I'm unpacking that tuple here into 2 variables, state and capital, and then I'm printing out the state and capital separated by an asterisk. Looping through the key value pairs in a dictionary wraps up our introduction to dictionaries, and dictionaries wraps up our introduction to 3 commonly used built-in data structures in Python. We talked about lists, we talked about tuples, which are immutable lists, meaning they can't be changed, and we talked about dictionaries, which are key value pair collections. Remember, there is an ordering to lists and tuples, zero-based indexing, but there is no ordering to the key value pairs in a dictionary. That's it. Thanks for watching.